Classification trees are a very powerful technique for classifying or categorizing our dependent variable. Now, one thing to keep in mind with classification trees is that because the objective is to, at each node, create a partition which splits the data into fairly uniform boxes, one can keep going and going and going till in the end we have pure boxes left. So we have only one category in a box. So we could start with our original data and then we could kind of split, and then we could keep splitting till in the end what we have are just nodes with completely pure categories. Now if we look at the accuracy of this tree, there would be 100% accuracy rate or 0% misclassification rate, because we have been able to filter down to each node or each terminal node having only a unique category. The problem with this is that we will not be able to replicate this in real life. We call this the overfitting problem. The basic idea is that if we were to use this tree, even though it does 100% accurate prediction for our training set, applied to new data, it may actually fail to perform. It will not do very well. That's because we have overfitted our model, and overfitting will lead to a low predictive accuracy on the new data. After a certain point, as we keep doing these splits, additional splits are not really bringing us any more information gains, or just bringing us only small information gains. And then the problem is that on the outside data set, this model will be performing poorly. So we always need to partition our data into training and validation, and even in test, so that we can build the model on training set and then see its performance on validation. So there's a nice graph which shows us the relationship between the splits and the error rate on training and on validation. So the blue line captures our training data set. So as we keep increasing these splits, we will eventually get to the point where we have pure terminal nodes without any impurity. But if we apply this model to external data or unseen data, very soon we see that the error actually starts increasing beyond a certain point. So our objective is not to best fit the training data, but to minimize the error in the validation set. There are two main approaches to achieve this objective. In the first approach, which is called the KIT or the chi-square independence test, we do not grow the tree to the full extent. At each split, chi-square test is run to see the purity of the records, and if after a split there is not a significant difference in the purity compared to the previous split, the tree stops growing. So this method is kind of, imagine the scenario where you are wanting to grow a tree in your garden, but you don't want a tree to go to a certain height, beyond a certain height, so you are just trimming the tree as it is growing. So the tree is never allowed to grow to its fullest bloom. In the second method, which is called pruning, and that's the more commonly used method, we follow the opposite approach. In pruning, the tree is first fully grown. So we let the tree grow to its fullest extent. In fact, in the end, we might have only pure nodes left as our terminal nodes. Then what we do is that we look at the validation set, and then we look at the accuracy in the validation set. We will be pruning the tree if the gains in accuracy in the validation set are not really significant. So let's say you prune a branch or prune a node, and then the accuracy measures do not deteriorate significantly. Then it means that that node was a weak branch and it could have been pruned. We move on to the next weakest branch, and the key is that at each stage we keep examining what branch to prune, and we look at some statistic, some sort of metric to see if pruning that branch did deteriorate our accuracy in the validation set or not. And then once we are satisfied with a pruned tree, we can then use that tree to classify or categorize our dependent variable on our third unseen data set, which we call the test set. So the validation was used to build the model, so the judgment is still a little contaminated. Now when we apply that tree to a totally new data set, of which we know the outcome, we can see how well it does on that test set. And then that can be an indicator for us on how our model might do on the external data. So the metric that is used for this is called the cost complexity, which is essentially a function of the error, and also it gives a penalty on the length of the tree. Now, JUMP will not follow the cost complexity criterion. It will look at a different metric, which I will introduce in a little bit. So what JUMP does is a combination of two things. It prunes the tree and also looks at the number of splits, minimum splits in a node. So we control the minimum split size, which says that how many nodes would be there in a tree before it splits. And then conversely, when should a tree not split? And once the tree is grown, it looks at the validation set and then starts pruning the tree. So it is kind of a hybrid approach of the kite method and the complete cart method, where there is some restraints put on the tree from growing. It doesn't grow completely to the last pure node. And then once the tree is grown with a minimum split size in mind, then it is pruned back based on the validation square, validation set R square. So this is like more of an automated process, and we will see how to implement this in JUMP. So how do we measure impurity? There are two common measures of impurity that are used in literature. The first one is Gini index, which is like a measure of inequality used in economics as well. And the Gini index ranges from a value of 0 to signify a split with completely pure categories in that split, to 1 where each category has an equal weight. So we are trying to find or minimize that method. The second metric that's used is called entropy. Entropy is in a way a measure of information. So the formula is pk, where p is the proportion of cases that belong to class K when there are multiple classes, and then it is multiplied by log to the base 2 of pk. Now entropy also ranges from 0 to the most pure class to log squared m. Now if there are only 2 classes, then log to the base 2 of 2 would be 1. If there are more classes, then this log base 2 of that class would be different. So in the case that we encounter most frequently, the 2 class case, the entropy would range from 0 to 1. Unfortunately, none of these measures are available in JUMP, because JUMP uses 2 other metrics to qualify when a node gets split. So in JUMP, we'll be using a measure of dissimilarity called G square or logworth to see where the split happens. But then the basic idea is still the same. We obtain an overall impurity measure of each individual split. At each successive stage, we compare this measure across all possible splits and then choose the split that reduces impurity the most. So now a tree, as nodes keep expanding, there are multiple splits that can happen. So what determines when the next split takes place? And this is again the split which would be reducing the impurity the most would be where the split would be taking place. And we will see that we can in fact predict when the split takes place next by looking at these measures like G square and logworth.